Welcome to our preparation lesson for the next major grade in the course, Lab 2.3. In this one, we're going to tackle a really big question. How do we know the age of the solar system? It's kind of a really deep question. Something that throughout the entire history of humanity, they've wondered, how old is the Earth? Biblical scholars tried to use the Old Testament to calculate based on the generations, going all the way back to the age, the week of creation, the 6 days of creation. And the number they arrived at was something like 6,500 years ago, the Earth was created. And that was the best information they had to go off of. Okay. But the challenge there is, we can't really blame them because they were using the best knowledge and resources they had available, the books that have been written. Now we have instruments, technology, scientific discovery, a process, this age of information to find out those important answers. So I ask you this. You can just accept that the Earth is 4.6 billion years old, or you can challenge the idea and say, convince me. How do we know that the Earth, and the solar system for that matter, are 4.6 billion years old? Let's tackle that question today. All right, so I'm going to guide you through this sheet that you see. It should have a 2.1 on the top, Radioactive Decay Lab. This is a prep page. You're going to be writing down some definitions. Now, you have the freedom to look these things up on the internet, or you can just keep watching this video, pause it every so often, fill in the blanks, move on to the next part that I share with you, fill in the blanks, and you'll be done by the end of this video. All right, let's take a look, shall we? All right. There's definitions, the top 4. You're going to be drawing a couple atoms, like the nucleus of the atom with the electrons orbiting around it. Make sure you get your numbers correct, because you'll find that the major part of understanding how we can determine the age of a rock sample. Maybe it's something from the desert, maybe it's a meteorite, maybe it's a piece of the moon. The numbers are very important. So let's start with the big ideas. So have your paper handy, okay? And if you don't have this in hard copy paper in front of you, feel free to swing by the school and pick up a copy, or go to Canvas 2.1 and print yourself a copy. Just open the PDF file, print it, and write down your answers, okay? All right. Without any further delay, let's do this. So, radioactive minerals have a lot of handy realities, handy features about them. The first thing is they decay over time. Now that can be dangerous, like if you're handling something with radiation, you've got to have your protective gear on. So safety is very important. But the science behind that decay is very informative. So what is radioactive decay? Things fall apart, give off radiation. But when they lose that little bit of extra weight, that neutrons trapped in the nucleus, we call that decay. And here's the cool thing. The decay happens at a set pace, almost like a racehorse going around a track. And you know exactly how long it'll take them to do one lap, and then they do another, exactly how long it'll take them to do another lap, etc. A race car or anything like that, okay? So we can measure that radioactive decay, and we do a simple calculation to find out, based on the amount of decay, how old is the sample. You can have a rock that is 10,000 years old, or you can have a rock that's 10 million years old. Radioactive decay and radiometric dating give us that information. Very cool stuff. Okay, so capture these definitions. I'll keep talking. Half-life is how we can measure the amount of time. If we understand what a half-life is, then all of this makes sense. That's what this lesson today, 2.1, is all about, understanding the idea of a half-life. The time it takes for half of a sample to decay and lose those extra neutrons. Okay. And then carbon-14, I'm sure you've heard of carbon dating. That is just one example of radiometric dating. That's the most common one people talk about because it's how we measure our own human history. Painting on cave walls, the bones of those who were buried 10, 20, 30,000 years ago, the charcoal in fireplaces that kept Native American ancestors warm 10,000 years ago. All of this is possible because of carbon-14 and carbon dating. Okay, so capture these details, capture these definitions, and then when you are ready, unpause it, and we'll continue discussing these big ideas. All right, moving on. So for number 5 on your paper, you'll notice there's 2 boxes. What I'd like you to draw is what you see on the screen right here. Carbon-14 and carbon-12, they are the same substance, right? They are basically the same material. It's almost like me if I were wearing my backpack, okay? I'm still Sandrock, I'm wearing a backpack. Except one of me is wearing a backpack, and if I take it off, it's still me. It's just me without my backpack. That's the difference between carbon-14, a little bit extra weight in the nucleus. Carbon-12, a little bit lighter, still carbon. Okay, so this is the difference. The nucleus of carbon-14 has those extra neutrons. And when it loses them, it becomes a different isotope, a different version of carbon. Still carbon, but it's a different version. I'm still Sandrock. I could be wearing a backpack, or I could not be wearing a backpack, and I'm still me. So I ask you then, after you do these 2 sketches that you see in front of you, what's the difference? The electrons are the same, 1, 2, 3, 4, 5, 6, yep. The protons, the little pluses, the protons are the same, 1, 2, 3, 4, 5, 6. But look at the neutrons. The numbers on your screen are different. The 2 sketches you're putting into those boxes are different. So there we go. There's the difference. Make a note of that difference for number 6. That becomes important later. All right. So when I mentioned the idea of a half-life, think of it like a class period. Okay? Our class periods are not exactly an hour, right? They're roughly an hour and a half, 86, 90, we'll call it 90 minutes. Let's just round it up to 90 minutes. So one class period is 90 minutes. So if you've gone to first period and second period, you've had 2 blocks of time that are called class periods. We just give them that label, class period 1, class period 2, put them together. You have 2 periods of time. Now, how many hours does that mean for 2 class periods? You can do this. How many hours? If it's 1.5 for first period, 1.5 for second period, together sounds like 3 hours. Okay? So 3 hours go by, that's 2 class periods. Now, hold that idea in your mind. The radiometric clock, carbon-14 has a time period, we call it a half-life, a time period of this many number of years, 5,730 years. So I ask you this, if 2 of those periods go by, it's not quite as easy as adding 90 minutes and 90 minutes, 1.5 hours times 2. This is now 5,730 years times 2. It's a good idea to practice this right now because you're going to be doing a lot of this in the next few exercises. So on your cell phone, right, open up your cell phone and go to the calculator. Okay, got my calculator up, and I'm going to do this with me. Why not, right? Do this with me. 5730, okay, times 2. So 2 half-lives, 2 periods worth of carbon-14, and I get 11,460. I think you probably got the same one. So 11,460 went by in years, but 2 carbon-14 time periods, we call them half-lives. 2 half-lives have gone by. All right, so hold that idea in your mind, and let's explore this in a little more detail. So make sure and write down what a carbon half-life, the carbon-14 half-life is. It's one of the things on your paper as well. 5730. All right, so we know that radioactive atoms decay. Carbon-14 happens to be radioactive, not harmful, okay? Here's how you know it's not harmful. You have carbon-14 in you. So do I. So does your dog. So does that tree outside. So does the breakfast cereal you ate this morning. Yes, my friends, your Frosted Flakes have a naturally occurring amount, and it's harmless, of carbon-14 in it. Because all living plants, trees, grass, vegetables, algae in the ocean, anything that grows from sunlight and breathes in from the atmosphere and grows like a tree or a plant, a bush, crops in the field, all those things create naturally a set amount of carbon-14. It's just part of being alive. And we, the humans and the animals, your dog eats his dog food, your cat eats the cat food, you and I have food on the table every night, and it either is like maybe a steak, right? Well, the cow that produced that steak was eating its grain, right? And its hay, its alfalfa hay through the winter. All that puts a normal amount of carbon-14. All right, so go with me on this idea. So numbers 7 and 8 on your worksheet. Carbon loses a couple of neutrons when it decays. So when a tree dies, it falls over and dies, it stops taking in more of the carbon-14. It's done absorbing it from the environment. And whatever amount it had, its normal set amount of carbon-14, that is the most it will ever have from that point forward as a tree trunk lying over on its side, dead on the ground and starting to decay. Okay. Not only does the bark and the leaves and the branches and all that start to fall apart, that's normal, but inside the tissues of that tree, you can take a sample, right? Take a look at this blue box. At first, when that tree falls over, and we grab a sample, and we're looking at it, and we're like, man, look, all of the carbon-14 is in this sample. And you put it on a microscope and you can look at it, or put it into a machine and it can count carbon-14. Okay, but then you leave that sample, you leave that tree there for 5,730 years. Half of the carbon-14 will have decayed. Half of this sample will have changed. Okay, and it won't be carbon-14 anymore. We can measure that, and we can take a tree of unknown age, calculate counting these little carbon-14 atoms, and determine how old it is. Let's do that together, okay? So in the beginning, all those atoms of carbon-14 are there, they're present, none of them have decayed, 100% is still there. Got it, okay? Now, we're gonna jump forward in time, step by step, taking this sample, okay? And then we're gonna see how it changes. Please note in the top corner, I've added a little legend. The dark blue circles, of which 100% are still there. This tree just toppled over yesterday. But if we jump forward in time, one half-life in the future, we expect half of this sample to decay. Let's go through this together. It'll start making sense. You'll be like, oh yeah, I get it. All right. So I will change half of the circles here every 5,730 years. Here we go. First change. 1 half-life has gone by. Half of the carbon-14 has decayed. So this is exactly 50% of that carbon-14 sample has decayed. Half of it is still carbon-14, half of it is gone. 1 half-life, 1 period of time, 5,730 years have gone by. All right, this is where it gets a little tricky. Stay with me. If your mind is drifting and you're thinking about trees in the forest, focus back on the sample now. Take a look at the sample. Watch. The half that is here now, I'm going to take half of that dark blue away for another half-life. Okay? So started with 100%, then went to half of that. Now 50%, I'm going to go to half of 50%. So you tell me, what is half of 50? If you said 25, you got it. Check it out. Let me show you the change one more time. Watch. 50% of that sample after 1 half-life. Now another half-life goes by, and half of that 50 is gone, and now we're down to 25% left. So picture this. If you were to have a sample of a tree that died a long, long time ago, and half of half, so 25%, if 25%, which is half of half, if it's gone and changed, you know 2 half-lives have gone by, and you know, based on carbon-14's clock, that this sample of an old tree that died ages and ages ago is 11,460 years old. Okay? Now, 25% is at this time frame. Let's take half again. Let's go to 3 half-lives. Here we go. Now I'm going to kick it another 5,730 years in the future, or after that tree died, and I'm going to take away half of the dark blues. Watch. Boom. Now half of them are gone. Now we're down to only 12 and a half issue. 12% of that original sample. I'm going to go back really quick to remind you. At the beginning, it was all 100%. 1 half later, half of it's gone. Another half-life later, another half of that is gone. Another half-life later, another half is gone. And it continues. Let's go to 4 half-lives. 3 half-lives, 17,000 years. 4 half-lives, 23,000 years. And the dark blues are fading out, and there's hardly any of them left. We're only at 4 half-lives now, after this tree fell over and died. Let's take it to 5 half-lives. Look at how much is left now. I took half of it away again. So 6% has now dropped to 3% of the original amount. Okay? Rather than do 6, 7, and 8 separately, I'm going to do all of them at once. We're going to jump 3 half-lives further down the line. And boom. Look what's left. 0.39%. Less than 0.5% of the original is left. So of all that carbon-14 that was originally there, less than 0.5% is left at 45,000 years later. And at that point, my friends, it gets really difficult to count a sample trace amount that tiny. Okay, our machines kind of reach the limit of what they can do at about 7 or 8 half-lives. So carbon-14 as a clock has kind of reached the limit of its usefulness. We started at 100%. Cut it in half, 1 half-life. Then we cut that in half, 2 half-lives. Then we cut that in half, 3 half-lives. Then we cut that in half, 4, 5, 6, 7, and 8. 5, 45,840 years have gone by, and the amount of carbon-14 remaining is barely a trace, 0.39%. Okay? Okay, let's consider what this really means, and we'll finish up what you've got on your worksheet. Here we go. Can we use carbon-14 to measure really long periods of time? Can I carbon date a T-Rex fossil? Let's compare some numbers now. Okay. If the dinosaurs died, how many years ago? My dinosaur enthusiasts, how many millions of years ago did that asteroid strike the Earth, kick up all the dust, darken the skies, and kill all the dinosaurs? Do you remember the number? All right. For your paper, the number that is accepted, 65 million years ago. Okay, so capture that for your worksheet. 65 million years ago, the dinosaurs were all wiped out. And we can't use carbon-14 because carbon-14 isn't a good enough clock. So if 8 half-lives, 45,840 years, if that is about the limit of carbon-14, can we measure dinosaur? Right? 45,840 is the limit. Can we really use carbon-14 to date a dinosaur sample? I would suggest to you it's impossible. Mathematically speaking, all the carbon-14 would be gone from that sample of the dinosaur. That when he died 65 million years ago, he had a normal, full amount of carbon-14 in his body. That's just life, right? But after about 45 or 46,000 years, there's not enough left to even measure. It's all gone. It's all decayed. There's nothing left. Okay? That, my friends, is radiometric decay. Okay? So please make sure you have all the blanks on this paper filled out completely before you move on to our next one. Okay? Your next step in our learning about this important idea is 2.2. Look in Canvas, Modules, 2.2. Have 2.1 handy, the paper you just finished. Have it handy nearby because you're going to take those important ideas as we develop and develop them further. And you, rather than watch me counting circles on a screen, you're going to be counting them yourself and doing your own calculations about the age of a sample. 2 of the examples that you do next time will be carbon-14. 2 of them will be an entirely different mineral, a different element, another radioactive clock. But the other clocks are better for much longer periods of time, handy for things like measuring dinosaurs and their fossils, handy for things like getting back to our original question, which is, what is the age of the solar system? How do we know the Earth and the solar system are 4.6 billion years old? Thanks for watching. I hope this has been entertaining and informative. And keep going with 2.2. Let me know if you have questions. Our class meeting link is on all the announcements. It's on every assignment. Just click on Google Meets. I'm here Monday through Friday, 8 a.m. to 2 p.m. And I look forward to seeing you face to face and meeting for all those mandatory classes we're expected to hold. So be there, and I hope you are doing well. Take care of yourselves, be safe, and look after yourselves.